Hello and welcome to the OLLI NOAA Climate Change Short Course. I'm David Herring, Director of Communications and Education within NOAA's Climate Program Office. And on behalf of NOAA and our partners in the OSHA Lifelong Learning Institute, it's a pleasure to bring you this lineup of world-class climate science experts to give an overview on our modern understanding of Earth's climate system. Today we're going to hear from Deke Arndt, who is the Director of the Climate Monitoring Branch within NOAA's National Climatic Data Center in Asheville, North Carolina, where he's worked since 2009, on preparing a monthly and annual series of reports known as the State of the Climate, which you can visit online at this web address presented at the bottom of your screen. And so with that, please join me in welcoming Deke Arndt, who's going to present the State of the Climate.
My name is Deke Arndt. I'm again at the National Climate Data Center, NCDC Climate Monitoring Branch, and we are the NCDC. If this is the commercial part, I guess, we're basically the world's weather and climate data library. So all of the observations that you see on the news or weather reports, those numbers live on in our archives. So the high temperature today for Fairfax will live on as a number somewhere buried deep in the bowels of the National Climate Data Center. And we use all that information to figure out, just like any good story, and our relationship with climate is a long and deep story. We want to know where we've been, where we are, and where we're going. And I know you got a good week of where we've been, and I think, as David said to me, this is kind of the where we are piece of this course. So thanks for having me. So we're going to just look at what is going on right now with the climate system compared and drawing on some of the historical things that you heard last week. All right, so how are we going to do this? We got, of course, a bunch of disclaimers and introductions and other minutiae to get out of the way first, and then we'll kind of start to unpack the climate system and look under the hood and recoil from how complicated it is, and then dive in there and really go kind of piece by piece for most of it, and ask what's going on, how do we measure that, and what does it mean in the bigger picture. And then again, how do we know the globe is warming? You know, we hear that a lot. The globe is warming. How do we know? What do we measure? And we measure many different things, multiple lines of indicators that indicate that the globe is warming. And then more so, how do we know that the warming that we've observed is driven largely or almost completely in recent years by human activity? How do we know that? We hear it a lot. What's the basis of that? And then finally, what else do we know about today's climate versus the recent past? And recent's kind of a loaded word in climatology. It could mean last month or it could mean the last ice age. But you know, how do we know, and what do we know more thoroughly on where our climate today stands against the climate that humanity has grown to adopt or adapt to? And so that's kind of the basis of this. There'll be a lot of graphs, and I hope if you're allergic to graphs, you might want to take your medicine right now, because we'll hit 5 or 6 to maybe even 10 graphs. And in climate and meteorology in general, we love maps and we love graphs, and that's really the best way that we know to communicate. And so I apologize in advance if you're not a fan of graphs. All right. So we're focused again on the here and now of the climate. This isn't really about calls to action or anything like that. This is focused more on the state of the climate system as a physical system. So there aren't going to be polar bear pictures, except for this one, which is just too cute to get away. You know, you got to have one. So yeah, that's a cute picture. So if you're nervous and you give a talk, you can always do a fuzzy animal, and that warms everyone up. So. All right, so this is the commercial. The Climate Monitoring Branch, again, is one wing of the National Climatic Data Center. And what we do is we watch the data as it streams in. So typically every month we will see all of the data from around the country and around the world come in, and we will attempt to glean some sort of meaningful, usable information for people that are sensitive to climate patterns, both in the U.S. and the world. I mean, essentially, you boil it down to its fundamentals. We write a lot of reports based on late-breaking climate information. Our mission is to monitor and assess the state of the climate. So before that high temperature today from Fairfax goes deep into the bowels of NCDC, we've looked at it in some way, and we've tried to incorporate that in a report that says, here's what went on this month in the U.S. Here's where it was dry, here's where it was warm, here's where drought had an impact, and we just try to basically report on the physical state of the climate system. In other words, we're the play-by-play guy. If you're a sports fan, that's kind of what we do. If the climate system is the game that we're all watching, we're just basically providing the play-by-play, what happened, where, and when, and we provide a little bit of this, the color commentary. So a little bit of what does it mean? Mostly what happened, and a little bit of, okay, drawing on our expertise as climatologists, how does that fit? How does that drought in Nebraska relate to the larger climate picture? The play-by-play person will say, there was drought in Nebraska. The color commentator will say, and that's part of an increasing trend of precip volatility, or a lot of rain falls at once, and it's expected that places in the interior part of the continent may see longer periods of time without rain or without significant rain. We're about 80% of the first guy and about 20% John Madden. We mainly report, but we do provide a little commentary. I also, if you're nervous, use polar bears. If you're kind of a chubby guy, you use John Madden, because you always want to be standing next to John Madden. Helps you out. All right, so a little bit about me. I'm a meteorologist. I grew up in an agricultural community in Oklahoma, a farming town. And if you're in agriculture, you understand the immediate impact of weather on the things that you do. It's really sensitive to weather, especially in the middle part of the country where you have a lot of hail and severe weather and high winds and tornadoes and stuff like that. So when you work in a farming community, you basically come to value the weather and our ability to understand and predict it. And so a lot of us from that part of the country grow up and do some meteorology. So my formal training in college is about jet streams and fronts and severe weather and all that kind of stuff that you see on the news. But then I got into drought for a really, really good reason. I needed a job, and the job that was open at the University of Oklahoma dealt with drought. And coming from an agricultural state, drought, it's a big deal. And so drought really introduced me to climate and how it's not just day-to-day or hour-to-hour weather that affects things, but droughts, it's a big deal, and that stretches over longer periods of time, months to seasons to even years in places. And then I got into climate through that same job. And then I got into kind of big picture climate, and that's what brought me to Asheville and the National Climatic Data Center. You can see the weather when you grow up around a farm. You can see how the weather impacts immediately what you do. You really don't get a chance to see the climate. You can kind of see its impacts, but these things change slowly, and you don't catch it every day. You don't go out at 4 p.m. and say, what's the climate doing right now? But it was an eye-opening role. We're so sensitive. We've grown up in this climate. We rely on our climate. We influence our climate, and we share our climate. And the realization of kind of going from a meteorologist that needed a job to working with climate. And this is even before we even talk about climate change. But working with climate, it's very essential to everything we do. It affects our food sources. It affects our energy patterns. It affects just about everything we do. And when you start looking at numbers, you really come to appreciate how fundamental this is to our livelihood. And then, you know, just I'm a meteorologist at my core, but that's only a tiny piece of the climate system. And one thing when we deal with climate that we've had to learn is we can't just have meteorologists in the room, or just oceanographers, or just biologists. You know, it's a really interconnected system. It's really complex, and you know, that's why that document that was placed online was enormous. And trust me, I think as the editor, I'm the only person in the country that read it from cover to cover. There's a lot in there, and it's connected, and we're just now beginning to understand many of those connections. All right. So this is the last of the commercial. The sources of data that you'll see in the next 45 minutes or so are from these three places. They're from that annual State of the Climate report, which we'll get into in a second. They're from the State of the Climate report that we produce monthly online, these monthly reports where we talk about what happened in the country and in the world. And you can also get these data from just a general climate monitoring. So this is drawn, if you want to go recreate or really dig into some of the data that we look at today, these three URLs are where you can go get them. And I assume this will be provided online, so you can come back and reference this if you like to get on the web and follow up. So this is where you can find this stuff. All right, so the State of the Climate report, the report that was mentioned just a second ago, this is a neat document. It's an annual supplement to the Bulletin of the American Meteorological Society, which is the professional organization for meteorologists in the Americas. So from Canada to Argentina, this is kind of where meteorologists convene and talk shop. So this report has grown from a 10-pager to, I think last year was about a 220-pager. That's basically an annual snapshot, an annual physical of the climate system. What happened this year in many, many different areas, and how does that relate to what's gone on in the recent past? So the State of the Climate report, it's peer-reviewed. So actually we're doing the 2010 report. We just sent those to the peer reviewers this week. So all of the chapters in the 2010 report are out there getting scrutinized by scientists around the Americas. All right, it's an internationally led and contributed document. All the green countries on this map represent where there was at least one author contributing to the report. So we got expertise from all over the world, and the red and orange dots are editors, chapter editors or document editors. So it again is short of the IPCC, the Intergovernmental Panel on Climate Change. This is kind of the little brother of that. It's an annual, just the facts, what's the state of the climate, what's going on, collection of reports from around the world. And it's broken up into several chapters. There's the global climate and the oceans and the tropics, and they all have processes that are different. You know, they're affected, they're related to the climate in different ways. The atmosphere, the oceans, the tropics, the water cycle, the processes where we get precipitation that falls into rivers, and we track river discharge, and just you can really examine the heck. It's like getting a physical for a long time, and they test just about everything, and you get a big report at the end of the year, and that's exactly what we're doing here. Really interesting stuff in the Arctic and the Antarctic, and then reports from the different regions of the world. So it was a real privilege to be on this document. There's about 250 authors on this coming document, and it's really intimidating. They're all really good at what they do, and I think being the editor of this document is like being the guy that gets picked out of the crowd at the NBA game to coach the All-Star team. It's really intimidating. There's really some leaders in their fields, and it's really neat to see all of that knowledge come together every year. So we're going to draw some stuff. Let's get into the climate. So this is something that was seen in that report. And you know, when we talk about climate change, the first thing people naturally think of is global warming, or the temperature of the planet. And that's exactly what this first graph is. And I'll use this graph as a chance to kind of walk us through the millions of graphs that we'll see in the next few minutes. They all go from sometime in the past, which is on the left, through the years to the current state, which is on the right. So this particular graph goes from 1880 to 2009. And they're often referred to some baseline period. And there'll be a positive or a negative number for whatever thing that we're looking at. This happens to be an index of the global average temperature. The zero line happens to be the 20th century average. So any year that has a blue crosshair on the zero line, which this is something in the early 30s, had a global temperature that was equal to the 20th century average. The farther up you get from the line, the warmer that year was relative to the 20th century. The further down you get from that line, the cooler the year was from the 20th century. Does that make sense? All right, so can you see a pattern in this data? Yeah, absolutely. So we're climbing into warmer, and each year, each crosshair represents a year, and we've been steadily warming over the last 130 years. A couple things to notice. First of all, there's a clear pattern that we are warming. Secondly, it's not the same every year. There's some noise in there. You know, if the long-term trend is like riding up an escalator, you know, we're doing some jumping up and down during that trip up. But you can see some years are warmer or cooler than others in their neighborhood. But when you pick any year from the early part of the century and you compare it to the later part of the 20th century, there's not many years in that neighborhood. So over the course of the last 130 years, we've kind of abandoned this neighborhood and moved on into this neighborhood, and then rapidly moved on into this neighborhood. Again, this is the average temperature around the world, all of the observations methodically combined into one global temperature index. Another thing is if we average these by decade, if we take the average temperature of the 1880s and the 1890s and the 1900s, and we do this for every decade that we've had, one thing that was apparent is that the 1980s, on December 31st, 1989, became the warmest decade of the instrumental record. And then every year of the 1990s was warmer than that average. And then on December 31st, 1999, the 90s became the warmest decade that we've ever had. And every single year in the following decade was warmer than that average decade's temperature. So at least for the last 20 to 30 years, the average temperature of the previous decade has been, at best, a baseline for the temperatures globally that we'll experience in the following decade. And 2010 came in right there, tied, according to NOAA, according to other places, first or second warmest year on record. And so this is, again, a global average over the course of the year, and the pattern is holding true that the first year of the 2010s is warmer than the average temperature from the previous decade. So that's, yes, ma'am. Okay, so the question was, how does 2010 compare to the history before this graph? There were warmer periods in the global temperature record. It's debatable whether any of those happened during times of modern human civilization. Yeah. And another point that draws out is the mechanism for this warmth is different than those we've had in previous warm periods. Those previous warm periods rose and fell over decades to centuries, and they were related to many things, primarily driven by the wobbles and idiosyncrasies of our orbit around the sun. What's unique about this particular period, if we are considering the deep history way off to the left, where there are several times when we've risen well above what we are now, is that we didn't have people running around depending on the climate. And also the mechanism, the driver for this is totally different than those. And it's much more rapid than just about anything we've seen in the past as well. Thank you, that's an excellent question. So this is what I call the grade school class picture graphic. When you're in grade school and they line you up from short to tall and take your picture, what we've done, this is the exact same data that was in the previous graphic. Instead of blue crosshairs, we have bars, and we've just lined them up from the coolest year to the warmest year. So 1911 was the coolest year that we've had in our 130-year instrumental record. And we go through to the warmest years, which were 2005 and 2010, off the end of the screen here. And all the years that happened in the last 10 years, we've colored red. So 10 of the top 11 years on record are red. They've happened in the last 10 years. The oranges have been in the last 20 years, 10 to 20 years, and then the greens have been in the last 30 years. And you can see when you line them up from cool to warm that we've stacked up all the recent years here on the warm side. It's just another way of looking at the exact same information. All right, so let's look under the hood, and this is so you'll see some flavor of this graphic in any meteorology or especially climatology textbook for undergraduates, and it just kind of walks through the many different interconnected processes, natural and otherwise, that affect the climate system. So when we're monitoring climate, we're thinking not just about global temperature. If we're just thinking about global temperature, we're being very short-sighted. But we've also got to think about things like, what's the status of frozen seawater or sea ice? How much water are we storing on the surface in our rivers and lakes? And how much of that is the atmosphere asking for in evaporation? And if we change the characteristics of either the rivers and lakes or the atmospheric demand for evaporation, and especially both, we're tweaking a little variable in this giant equation here. And so when we talk about climate monitoring or the climate system or climate change, it's really easy to get hung up on the global temperature as some complete indicator of what's going on. And the truth is, it's really complicated. To the best of my knowledge, no one has ever been found dead under a trace of the global temperature. You know, it just doesn't do that. But all of these things that are related to it, that does harm people and economies in commerce. And it helps people and economies in commerce as well. So it is a complicated system, and it's really not the global temperature that's going to do the harm or the benefit. It's the ripple effects of that. It's the connections between it and the larger system. All right. So this is my report card. Recognizing the complexity of this system, this is what the BAM State of the Climate is asked to monitor. There are 42 variables up there in different colors. There are 6 that are related to the atmosphere: temperature, precipitation, air pressure, the upper atmosphere, water vapor, different things about the types of gases that are in the atmosphere, the state of the near surface ocean, how salty is it, how's the water moving around, what's the temperature, what's the sea level, the state of the deep ocean, how salty is it, how's it moving around, what's the temperature, and then a lot of stuff that we've thrown into a category called terrestrial, which is at the interface between the land and the atmosphere. And those are things like what's growing where, how much water is being discharged from rivers into the oceans, and how much permafrost is there. And the report card for the BAM State of the Climate report is how many of these can we completely observe and report on them in a reasonable amount of time, within a year or so. So where you see green, the scientific community, or at least the BAM State of the Climate document, is completely kind of globally monitoring these in a way that is meaningful for global trends. Where you see yellow, we either do not have a sufficient set of observations to completely monitor them, or we just recently deployed those and we don't have a long enough period of record to kind of compare to history. And where you see red, we just don't have sufficient data to make global estimates of these things. So the report card, we've been slowly turning these green over the years as a scientific community, sharing a lot of data, rescuing a lot of data, finding new ways to capture information about these through observations. And when we get all of these green, depending on your faith posture, that's either being on target, X marks the spot, the promised land, or the holy grail of climate monitoring. So it's our job to try to monitor as much of these as we can. This is what goes into the BAM State of the Climate. Thankfully, we won't be diving into every single one of those today. So if you want to go play with those, one of the previous URLs, you can click on Key Climate Indicators, and this is the nasty 5 straight graphs part of today. So one of the things that we did, because the global surface temperature record, in the public anyway, is very controversial and has a lot of stuff flung at it, we decided, let's pull that aside and let's look at 11 other indicators that are related to the global surface temperature that are not as controversial, and let's see how those are behaving. And of those 11, 7 of those we would expect to be going up in a greenhouse warmed world. 4 of those we would expect to be going down in a greenhouse warmed world. And this is really kind of the centerpiece of that document last year. So we looked at things like land surface temperature, so the land piece of the global temperature, sea surface temperature, the ocean piece of the ocean surface temperature, temperature of air over the oceans, which is different than that global surface temperature, sea level, tropospheric temperature, which is, we're going to build for the first time our model of the atmosphere. The troposphere is the bottom slab of the atmosphere. It's the one we live in. It's the one where all weather occurs. So the temperature on average throughout the troposphere, it's about 30 to 40,000 feet tall from the surface to the top of that layer. That's where we live and do business. So not just the surface, but the temperature of that whole level measured by satellites. Ocean heat content, literally the amount of calories or joules, the amount of energy that's in the ocean's top 700 meters. And specific humidity, which is a fancy way of saying humidity. How much water vapor is in the atmosphere and how's that changing over the time. If the global surface temperature record is legitimately going up, we would expect these 7 to also increase. We would also expect these 4 to decrease, and they mainly deal with frozen stuff. Snow cover, sea ice extent, the amount of volume or mass in our planet's glaciers, and the stratospheric temperature, and we'll get into that in a second. But if we have the top of the troposphere, the next layer up is the stratosphere. Sometimes we poke into there when we fly on really, really long jet flights. But we would, for reasons that we'll get into, expect the stratospheric temperature to also decrease. Does that make sense? Okay. All right, so here's the graphs. This is from 1850-ish to 2009. This is the air temperature over land measured by weather stations. And these are 1, 2, 3, 4 different data sets that compile a global average over land. And although there are minor differences between these data sets, they're all in unanimous agreement. They may sing off key, one note here and there with each other, but they're singing the same song. The global surface temperature over land is increasing. The temperature over the oceans, measured by buoys that are out there in the distant oceans, how are those changing over time? These come from buoy reports and ship reports. Again, they may they may harmonize a little on the individual notes, but the song is the same. Since the latter part of the 20th century, there's an increase. And there's also some similarities before that as well, too. Global ocean heat content starts at a much later period. So instead of 1900-ish over on the left side, we're talking about 1950-ish. And this is an important one because the vast majority of the warming of the planetary system is going into the oceans. What we're observing over land in our weather stations is only a piece of the total amount of energy that's going that's being trapped near the surface. You know, water can hold a heck of a lot more energy, or has a lot more what we call thermal inertia than air. And you can see that by sticking, in Oklahoma anyway, we had the old twisty ice cube trays. You know, you make 12 to 14 little ice cubes, fill them up with water. You stick them in the freezer. Do they freeze immediately? No, it takes a while, right? Now, you take one of those ice cubes out of the freezer, you stick it on your counter, and does it melt immediately? It starts to melt. It takes a long time to melt. Water takes a lot more energy. You have to invest a lot more energy to raise the temperature of the oceans just a little bit. And when you start measuring the amount of that energy, what we're doing is we're looking at what is essentially a savings account of the climate system. That warming that we see kind of reflected in the atmosphere, over the land and over the oceans. Well, when you start thinking about the energy in the top layer of the ocean, if these measures are kind of unanimously agreeing that those are going up, we are basically looking at the savings account of warming in our planetary system. Yes, sir?
You said that depth was about 700 feet.
700 meters. This is in the uppermost 700 meters of the oceans. Yes. Oh, these are in, this is the zero line, so this is an average from about a 30-year period here. And believe me, this is as meaningless to me as it will be to you. These are in joules times 10 to the 22nd. So this is 5 joules with 22 zeros after it, as how much extra energy compared to this average here. It's a measure of calories or joules, or a measure of energy. And finally, just one more example, sea ice in the northern hemisphere. This is the September average sea ice extent. September is when every year the Arctic sea ice footprint is the smallest. It retreats over the summer to a minimum in September. And we take that monthly average and we see what it's done each year. And in recent years, September's sea ice extent has been very low, which would be consistent with a warming world. But none of these by themselves or even together indicate that this is a greenhouse warmed world. All of these just say, yeah, in the last several decades, the world's gotten warmer. And that's really all that these data sets can say. Now, they say it very convincingly together. They say it in concert. They're in unanimous agreement that the world is warming, but they don't say anything about why or what's driving this. And that's where the next data set is critically important. It's the stratospheric temperature. So everything that we live down here on the surface, and we have a troposphere that's 30 to 40,000 feet thick. And on top of that, we have the stratosphere that's another few tens of thousands of feet thick. And the fact that the troposphere is warming, but the stratosphere is cooling, tells us something really important. It tells us that the whole system isn't warming. It's not something like the sun is getting brighter and the whole planet is warming up, or because of our orbit, you know, we're getting a little closer to the sun now, or we're tilted in a certain way to cause some warming. It's not unanimous through the system. So what's happening, to the very, very best of our knowledge, and this we feel the scientific community's pretty locked onto this, is that heat, that warming that we're seeing in the lower part of the atmosphere at the expense of the next part of the atmosphere has to do with heat trapping gases. The atmosphere is trapping more heat closer to the surface, and it's raising the marine temperature, and it's raising the land surface temperature, and it's melting the sea ice, and it's also preventing that heat from getting up here in the stratosphere. So if there is a smoking gun in all of those, this is it. This is the one that says, yeah, things are changing down at the surface, but the whole system isn't warming up. It has to do with the composition of the atmosphere. And I'm sure you'll have, like Tony next week, who's a brilliant guy, get a little bit more into those processes. But this is important. This is the smoking gun. This is the one where you go, okay, yeah, something's going on. And and we're warming. And then just to put it into a cartoon, these are the exact same variables, and where you see a white arrow, that measure is going up, and where you see a black arrow, that measure is going down. All right, so that's kind of the global picture from that document, and then this is just kind of an update. That was all through 2009, and we can't show the official stuff from the BAM State of the Climate for 2010 because it hasn't been peer-reviewed, but we can show you some preliminary stuff that my office looked into from 2010. And this comes from the NCDC State of the Climate Report. This is a service that's mandated through NOAA. So we are mandated, go write reports about the climate. And so we do monthly reports on all of these different issues on a global scale and on a national scale. So 2010, in addition to being first or second or tied for the warmest year on record, depending on the lens that you look through, it was also a wet year. It was astonishingly wet in the tropics. It was wet where the wet got wetter and the dry got drier in 2010. And while that doesn't happen every year, that's consistent with what we understand about climate change. We expect that on average, but not universally, the wet places will get wetter, the dry places will get drier, the wet seasons will get wetter, the dry seasons will get drier. Again, it's not universal, it doesn't apply everywhere, but in the big picture, that's what we saw. So what we're looking now is a dot map, and where you see green dots, those places were wetter than their 20th century average. And where you see brown dots, those places were drier than their 20th century average. And the size of the dot just tells you how much wetter or how drier it was. So we saw really active tropics and subtropics in Asia. We saw southern part of Mesoamerica really, really wet. There are actually a lot of tropical cyclone landfalls down here. And then we just saw Australia. We all followed that. Over November and December and January, the wetness that they saw that. Now this isn't an indicator of climate change at all. This is just adding 2010 to the greater picture. But one thing that was interesting was when you average all those dots together, at least over land, and this doesn't include oceans, the land observation said this was the wettest year that we've had on record since 1900, which kind of didn't make it out there, but it's kind of a big deal. Again, no one was ever found dead under a trace of global temperature, but if it was on average the wettest year on record over land, there were lots of people dealing with a lot of water at once. And we did see some unusual flooding in parts of the world like Brazil and Australia and many places. Arctic sea ice extent, just an update on that. The last 2010 data we had was from December, and it was the smallest footprint, so it was the most below average of any year since the satellites have been measuring these, which started in the mid to late 70s. And then tracking stuff. These are all kind of global or quasi-global things, but again, there's a lot of stuff that happened. I won't even pretend that anyone can read. This is just kind of a play-by-play of the big things that happened this year. A few points. There weren't many tropical cyclones this year. It was a very, very inactive year for hurricanes and tropical storms globally. The Atlantic was very, very active, but it was the only basin in our ocean that was active, and then a lot of those storms ended up hitting again, the southern part of Mesoamerica. What else happened? All right, so we're drilling down. We were talking about eras and epochs and decades and centuries, but let's talk about episodes and events, things that we can go out and feel and touch that affect us every day. What's happening with episodes and events? Instead of worrying about the average temperature, the average precipitation, or the average sea ice, one of the things that we need to do a better job of in the climate monitoring community is tracking the things that affect people in real time. And that stuff we often call weather. So what did the weather do in the last few years? And this is where our first literature review, I couldn't do a talk without a literature review. So Stallone and others wrote a great piece of literature that really, really defines the relationship between climate and weather. And that was this. This is how climate and weather are related. This guy's weather and this guy's climate. Climate trains the boxer, weather throws the punches. And so when climate change, it's not just an esoteric line on a graph. You know, climate will train weather to throw certain punches more often, more effectively, less often, less effectively over time. When you change the trainer, you change the pattern of the punches that are thrown. And so that's what we're really getting into in climate science, is how are these punches changing? So El Nino and La Nina, everybody's heard of El Nino. El Nino for a while in the 80s and 90s got blamed for everything. And El Nino is just a way of measuring, among other things, the temperature of the tropical Pacific Ocean in the eastern, most of the tropical Pacific Ocean. And when this area is really cool, we call it a La Nina, and it has certain ramifications on kind of seasonal expectations around the world. And when it's really warm, we call that El Nino, and it has ramifications on kind of seasonal expectations around the world. And we have a million different ways to measure it, and we love to make indices to measure these things. So this is just one index. The methodology's a big nasty mess on how we arrive there, but basically when this index creeps up above this line that's a little difficult to see, we say, yes, we're in an El Nino. And when it creeps down below this line, the index that we calculate, then we say, yes, we're in a La Nina. And 2010 was remarkable in that we began the year in a pretty dadgum strong El Nino and ended the year in a really profound La Nina. Actually, one of the more impressive La Nina events that we've had in a while. All that flooding in Australia probably related to La Nina. The dryness that the Gulf states and the southeast and a little bit of the mid-Atlantic has seen later this year, that's kind of classically related to La Nina. So the only reason to throw this on here when we're talking about the state of the climate is that there's a phenomenon that happens and we think it's important, and we've invented some index to track it. This is the Dow Jones Index of El Nino. But there's a lot of these sloshing patterns, and what happens here is this is a part of the world that typically has easterly winds. And during a La Nina, those easterly winds increase, piles up this thin layer of warm water over in the western part of the Pacific, and cooler waters emerge in the eastern Pacific, and that has all kinds of domino effects. In an El Nino, those easterly winds relax a little bit, and that warm water just sloshes back and occupies a great deal of the eastern Pacific. And I promise there's a point here. The point is, it's a sloshing thing. It's a sloshing pattern. It tends to take 2 to 5 years to kind of go through its oscillation. The O in ENSO, El Nino Southern Oscillation, it's not regular, but it takes, these things happen in patterns of 2 to 5 years. But there's a lot more of these that actually have pretty more dramatic, direct, immediate impacts. It's just that El Nino is the biggest one and it has the most global reach. One of these other kind of sloshing patterns, not just in the oceans but in the atmosphere, is something that we call the Arctic Oscillation. And it basically measures the relationship with air pressure from the poles to the mid-latitudes where we live. So it's a measure of, do we have a lot of high pressure over the poles and low pressure at the mid-latitudes? That tends to create a lot of jailbreak situations where cold air spreads southward. We've had a lot of experience with this in the last couple winters. So anybody remember February of 2010? That was pretty fun around this part of the country. That was the most dramatic of this particular oscillation index that we've seen since we've known how to measure it. We also had one in December of 2010 that was pretty impressive. And what happens when the Arctic Oscillation Index gets funky, it gets way down here, is we do see a lot of episodes of really cold air outbreaks over parts of the world, and then in order to replace that cold air, a lot of really warm air escapes northward in other parts of the world. So in January and December, when the eastern half of the country was getting creamed by all the impacts of cold air, remember what was going on in Vancouver at the Olympics? Didn't have any snow. It was really warm there. And so that was an example of when the Arctic Oscillation gets strong, we move a lot of air northward and southward. Well, one thing that's interesting about this graphic is, what do you notice about the last 15 to 18 months on here? Does it look the same as the rest? It actually, if you kind of hold your eyes and squint, it looks like this looks a little different than the rest of the pattern. And it could correct itself next month. There's a whole bunch of research going into what's up with the Arctic Oscillation. We'll see a million papers coming out. They'll say a million different things. And eventually we'll get to understand what's going on with the Arctic Oscillation. But part of the reason that we've had some of the more severe outbreaks is that the Arctic Oscillation is behaving in a month-to-month way that is different from the known record. It's diving deeper into that negative territory, and it seems to be doing it with a little more regularity. Again, it could correct itself out of that tomorrow. I'm not an expert on the Arctic Oscillation, but when we monitor these things, it's important to go, wow, that's unusual. So here's another measure of the same thing. It's called the North Atlantic Oscillation. It measures the same thing, but with a longer record. And again, a lot of noise, boom. So one big question, these do things. When we have really negative NAO or Arctic Oscillation, we see a lot of cold air outbreaks. And again, it's way too early, and I'm not the person that would determine whether we've had a regime shift. That would be someone much more specialized and smart. But if there is a regime shift, this is kind of what it looks like. It goes from one state to another. And that's, we will probably in the science community see a lot of research on what's going on with these two indexes. All right. I promise we're near the end here. This year we had a dramatic El Nino, warm water in, I'm talking about 2010. January 2010, El Nino. December 2010, La Nina. Those are supposed to govern our winter weather. In the absence of everything else, the long-term forecasts are really sensitive to El Nino and La Nina in the winter. It's actually got some skill. They're a little better at forecasting things for the season when El Nino and La Nina are kind of strong. But we also had this really strong Arctic oscillations, and what that did was we had some massive cold air outbreaks in Europe and Asia that kind of were much more related to that Arctic oscillation. So the point of this whole last 3 slides excursion into this really bad neighborhood of Arctic oscillation is to point out that there may be a new oscillation index behaving in ways that we haven't seen before that has a more direct impact on our winters and a much more predictable impact. Now it kind of goes up and down in the scale of weeks where La Nina and El Nino take a couple years, but in the science community, the way we would say this is if El Nino, La Nina, and the Arctic Oscillation got into a knife fight, bet on the Arctic Oscillation. You know, if you live in the northern hemisphere, the Arctic Oscillation is going to govern your winters a little more. And again, how does this relate to climate change? That little downtick at the end is, if nothing else, very interesting. All right. The U.S. just happens to be warming at the same rate as the rest of the globe. with a lot more noise. We're a much smaller patch of ground on the planet. But this is that same graphic for the United States temperature. We're also warming at about the same rate. We also just finished our warmest decade in the US instrumental record, which started in the 1890s. But we haven't seen the consistency. We're not as consistently warm. We still have cool years and warm years, and that's what we would expect, only taking up 2% of the planet. We're still going to be influenced by weather. This is what that looks like. We had a really warm year in the mid-Atlantic, a really warm summer in the mid-Atlantic, extending up into England. Parts of Maine and eastern New York had their warmest year on record. And parts of Florida and southern Georgia had their coldest year on record. Again, a year dominated by a pattern where a lot of cold air surges southward and a lot of warm air surges northward. Average them all together, the year as a whole, it was kind of warm, but it wasn't real impressive. But the way it was carried out, was, this is pretty dramatic. And it's interesting, and this is something we're keeping track of. Again, very dry. As one might expect in a La Nina year, much of the south and southeast was dry, starting to deal with some water problems in the deep south and the mid-south. And then finally, we talked about kind of weather and climate, and the last index that you'll have to suffer through a graph on, I think, is this Climate Extremes Index. And what this is it's attempting to measure how extreme is our weather becoming. How much, and technically what this piece of it is measuring is how much of the United States for any given month, or this is summer, for any given summer, is under the influence of what we would term extremely warm minimum temperatures. Overnight low temperatures, how big is the footprint of extreme warmth and overnight lows during the summer? And overnight lows are really important in human health. If the temperature doesn't go down into the 60s or 70s in places that are used to it going down to the 60s and 70s, that can have some human health impacts. It has a lot of horticultural impacts, and it has some agricultural impacts as well. And so what we've seen from 1910 to this last summer is a pretty clear trend of increasing areas of the U.S. experiencing extremely warm overnight lows during the summer. And we could play a game and say, this is weather, this is weather, this is weather, this is weather, this was weather, and it was. This was weather. These were kind of weather episodes that set up and camped over much of the U.S. But eventually the climate people are going to have to come back and say, yeah, but this is climate. This is a fingerprint of a changing climate, is that weather episodes are becoming more frequent over the long term. You can't tell because of the trainer what the next punch is going to be, but if we fight 10 more rounds, the guy's going to throw the left hook a lot more often. And that's what climate's doing here. The change in the climate that we've seen in the U.S. has expressed itself as overnight low temperatures during summer, which are really important, are becoming more extreme more often. This is just a laundry list of states that had their wettest or driest or warmest whatever on record in 2010. So a lot of states had their warmest warm season. Many states had their warmest summer. Wisconsin had some really wet seasons. These are the warmest or wettest months. Florida got into the act by having its driest October, its coldest December, its driest fourth quarter, its warmest. It was all over the place. There's a coldest in there too with Florida. But we did see it. 2010 was a year of extremes, it's evident here. And then finally, this is the last good picture. Another extreme that we had this year was the largest hailstone that's fallen in North America. And that's kind of fun, and I have a cast of this on my desk. It's great, a plaster model, and it weighed 2 pounds. And The thing that was strange about this summer is this 8-inch hailstone was the largest hailstone on record in the United States. We had 2 that would have broken the national record this summer. And one thing that to think about, and this is stretching a little bit, but thunderstorms become more intense and more violent in the plains and anywhere when you have really warm and moist lower atmosphere and a really cold atmosphere above that. That means, what is a hot air balloon? You make a hot air balloon hotter and it rises. You make the lower atmosphere hotter and more moist and more buoyant, and it's going to rise more quickly, and it's going to hold up larger hailstones. Again, I'm not scientifically connecting the dots, but this summer when we had lots of really, really large hailstones reported, and we had to do a lot of state record hailstone and national record hailstone investigations, that was the thought that crossed my mind. When we talk about climate change, we're talking about this escalator effect. The climate and the global temperature and all of the little pieces of climate are going to jump up and down on a trampoline. They're going to have cycles of various length, and we did see some cooling and some warming in the early 20th century, kind of leveled off, and then in around the 70s it took off again. So we are going to see, again, those ups and downs. We expect those to continue even in a changing world. It's just that we're jumping up and down on an escalator now. So the ups and downs will be expressed on a tilt rather than on a flat line. Did that answer your question? Okay. I do not do spectral analysis of these time series. That's a physics type approach, and we are mostly doing statistical approaches to these. It is done in the scientific community, but from a monitoring perspective, no, we don't. Yeah, that's a kind of a really late-breaking kind of flurry of papers and research in climate science, and the basis of this is, would a retreating summer ice footprint, as we start to expose more and more open water in the Arctic, will that somehow affect the Arctic Oscillation that we talked about and lead to more dramatic cold air outbreaks? The science is really still being done on that. I don't think we're at a confident place on that. It is interesting. One thing that we've talked about that paper a lot in the last few months. But we also had, not nearly as dramatic, but we had in the late 70s and the early 40s some really dramatically cold winters. And as far as we know, we do know in the late 70s there was a lot of ice when those happened. So I think most of science is really interested in what that comes up with, but it's really early in the process to say with any confidence that that's having an impact. And I'm sorry for the wishy-washy answer, but that's where we are. In the BAM State of the Climate, and I'm an old meteorologist, so oceanography is pretty new, but our Oceans chapter is seeing evidence. Really the most striking thing about the ocean circulation that we're seeing is the salinity profiles. Currents they do have a lot of variability, and we aren't equipped to measure them globally really well. That's an expensive endeavor. But the salinity profiles that we're seeing, the salty parts of the ocean are getting saltier, and the fresher parts of the ocean are getting fresher. And the physical connection for that is the water cycle seems to be accelerating. The salty parts of the ocean are associated with areas where it evaporates more water than it receives, so it leaves a saltier ocean behind. And the fresher parts of the ocean occur in areas where more precipitation falls or runs off than evaporates. And we are seeing a pretty consistent pattern in recent years that that is indeed the case. That is a fingerprint. It's not the only signature, but that's a fingerprint of a hydrologic cycle, a water cycle that's accelerating. Gases in the atmosphere are essentially trapping heat lower in the atmosphere at the expense of the upper parts of the atmosphere. It's maybe not coming from the stratosphere, but in a big picture sense, the additional heat that we're seeing low in the atmosphere is coming at the expense of heat that would typically be...
Well, it's not escaping then to the
Yes.
stratosphere.
Thank you.
Okay, thank you.
Thank you for putting that in English. Yeah, that's a great question. And the density and the consistency of the stations is constantly changing. Throughout the U.S. is pretty stable. Throughout the world, we saw a golden era of observations in the middle part of the 20th century, and since then we've had fewer stations. For the composite global temperature index, the ways that we account for that are there are mathematical techniques that examine for breakpoints in a station's relationship to neighboring stations. So for instance, an example is Reno, Nevada. We found that the scientific community that's much more intelligent than me found that the temperature sensor was moving up and down the airport runway in Reno. If you've ever been to Reno, the north end of the runway is the casino district, and the south end of the runway is in alfalfa. So you've got hay bales, a mile and a half from the MGM. And one of the ways that was detected was when the station was moved from the cool part of the runway to the warm part of the runway, it really showed up in its relationship with neighboring towns. Like Reno used to be a little cooler than the neighbors, and now it's a little bit warmer. And so there are actually statistical techniques that go through and find breakpoints and correct for them when they're large and obvious. The other way that we do that is the dot maps that were on here earlier are 5 degree by 5 degree latitude by longitude grids. And that is a composite of many stations within that grid. And one of the things that is really misunderstood, and we don't do a very good job of helping people with at all, is when we construct a global temperature index, the first thing we do, other than throw out, egregious temperature errors like minus, 999, the first thing we do is convert that month's temperature at a state. We'll use Fairfax for an example. We convert the Fairfax March temperature to what we call an anomaly, the difference from the average March temperature in Fairfax. So the average March temperature in Fairfax, let's say this year it was 53.5 degrees. That gets converted from 53.5 to let's say the average temperature long-term for March is 50. It gets converted to a plus 3.5. Does that make sense? So we take the very first step we do is we convert the temperature to relate to its long-term average. And what that does is when you lose stations, if you have a station in a valley and a station on a mountain, they're going to have completely different histories. This valley station may hang out in the 60 degrees in March, and this mountaintop station may hang out climatologically in 40 degrees in March. So when one station drops out, you think, oh no, the warm or the cold station is going to compensate for the other one. But converting those to anomalies, because the relationship is that even though this station is reporting 60 something and this station is reporting 40 something, if it was a warm month here, it was a warm month here. And so when we do have differences in the station distribution, one of the things that we do to account for that is that we immediately convert. We only use stations that have known long-term histories, and we immediately convert them to anomalies because we know that those are much more robust. We can do mathematics with a much straighter face when we use those anomalies. And there are other techniques to detect undocumented station moves, and thankfully most of the station moves are documented. And when a station moves, it goes from being one station to another in our records. So if the Fairfax station were to move across the county, it would become a new station with its own history, and it would have to work for about 30 years to establish a history before we would use it in a sensitive climatological technique. Now, the day it moved, it'd still be valuable for the weather people. The forecasters would still love to know the general temperature and the winds, but for sensitive climate stuff, we can only use stations with known long-term behavior and adjust for obvious adjustments from that behavior. Yes? I'm hesitant to, because I'm not an expert in food and water supplies. I do know that many places in the world rely on glacial water for their community's water source, at least during certain seasons of the year. And in general, glaciers are retreating around the world, but not 100% of the glaciers are retreating around the world. I could give you an answer, but it would be no more authoritative than it would just be my opinion. So, yeah. Millions and close to billions for some of the long term, but so for the global surface temperature, the land part are weather stations that have been reporting for a long time. The ocean sea surface part, I'm from NOAA. NOAA uses ship reports and buoy reports over time. Some other agencies, NASA actually includes a satellite element to that as well. For the troposphere, it's tricky, and again, we don't have data going back in the 1800s, but we've been launching weather balloons for a long time. And when you deploy a weather balloon, it's a helium or hydrogen-filled balloon with a little instrument package underneath it, and you let it go, and it samples all the way up, and then the balloon pops, and a parachute comes down to the ground, and sometimes it can land on people's homes, and they call the police because there's a strange package on the roof. But we've been doing that for a long time, and that measures standard levels in the atmosphere. And so that's the basis of our tropospheric and some of our stratospheric temperature record. But what we found is satellites have the capacity to observe the layer, and that's what they're actually really strong at. That the advantage that we get from satellite observations is it's not just a balloon point source. The satellite can actually see a bigger piece of the Earth, and there are ways to sample the temperature, the average temperature, at points at every little pixel, every point on the map. So the tropospheric and the stratospheric temperatures are largely driven by satellite data. They're more spatially complete. They're kind of linchpinned to the historical record by the radio or the weather balloon data, and that's generally what we use. I'd also say that the surface temperature record is based on daily observations, almost unanimously around the world. Not everyone has the luxury of getting hourly data like we do in the United States and Canada, but many places, for agricultural purposes, and traditionally in the US, this is how we observe it, and still do in many places, we take a maximum and a minimum temperature each day of the month. We average those two numbers, and that's the average temperature for the day. And we take 30 or 31 of those average temperatures for the day, and we come up with an average temperature for the month, and then we convert that relative to the month's history. So there are, in real time, so the monthly reports that we report online, we'll have about 2,000 stations around the world. For the deeper record, and when there's time for the data to come in, we get up closer up into the 5,000 to 6,000 stations around the world, which is plenty good for constructing a global temperature index. Yes? I'm wearing not my science expert climate monitoring hat, but the guy that likes to read climate papers hat. There's a lot of really good research going on in that. And yes, there are many positive feedbacks that things are accelerating. Sea ice is retreating at rates that are more than kind of prior. The projections for the retreat of sea ice are catching up to the reality. Let me put it that way. And again, that is a positive feedback. The less ice cover that you would have at any given time in the year, the less sunlight that would be reflected back out into space, and the more that would be absorbed into the system. So there are several positive feedback mechanisms like that. You know, one real unknown in climate science, in the modeling community and the observational community is really going after this is, yes, it's clear that there's more water vapor in the atmosphere. The question is, what type of clouds do those make? If you make a lot of high thin clouds out of that, or do you make a bunch of puffy, really white clouds? And the feedback for that is unknown, and that's kind of the next big step in really improving our confidence in the projections for the future. Is getting a handle on what types of cloudiness and characteristics will we get out of an increasingly moist atmosphere. Yes? Tremendous amount of work has gone into that as well, far beyond my expertise. I'll say that 2 degrees Celsius, a rise of 2 degrees Celsius was established about a decade ago. I can't remember exactly when, by the IPCC and other multinational approaches as, yeah, that's a big deal. So based on research, not just in climate system and physical climate system, but also a lot of work with other systems, human health, agriculture, forestry, ecology. That was established as kind of a target, as that's a big deal. Now, is there something magic that happens at 2.0 degrees Celsius? Probably not. But the more that the temperature increases, you get an increasing likelihood that several of these subsystems may spin off and start doing things radically differently. And you know, that's where the whole tipping points and all of that conversation comes in. So there's nothing magic about 2 degrees Celsius. There's nothing radical, to the best of our knowledge, radically different about a global temperature increase of 1.99 degrees versus 2.01 degrees. But it has been fairly established that a target of 2 degrees Celsius is kind of a big deal. Does that?
I was really getting from what's the statistically meaningful change? And given the changes in measurement technology and all these other things, how much do you have to, at what point is it really a statistically meaningful?
It's statistically meaningful now. You know, with statistics, it's the same process of establishing how confident do you want to be. You know, kind of traditionally it's 90 or 95% statistical confidence that a change has occurred. So the fact that a change has occurred in the last 130 years or so, that's very confident. It shows up not only in the global surface temperature record, but in all these other conditions as well. Now, as far as accommodating the multitude of different observing platforms and technologies that we've seen in the last 130 years, we've seen several evolutions of how we observe things, even when we observe things during the time of day. Those are attacked by teams of people that spend their careers in blending, okay, what does it mean when we have a liquid in glass, an alcohol or a mercury in glass thermometer in a wooden shelter versus an electronic thermistor in a little honeycomb apparatus on a pole, And they've done lots of research, side-by-side comparisons, and understanding the relationship between different methodologies, to the point where they can say, we would know over time, not on a particular day to day it's different, but statistically over time, that when we see behavior like this in this wooden shelter, cotton region shelter is what it's called, and this thermistor, that we know the relationship between that, and we can fairly confidently correct for the difference in these two methodologies. That happens a lot in a station's individual history. You could see, if the station started in 1898, they were using mercury or alcohol in a glass thermometer, and then they switched to, in the 80s, there was a big switch to electronic observation. You can see that in several stations, and thankfully, there were enough of them side by side being practiced at the same time that we could establish, quote, transfer functions between the two. Yeah. Ocean circulation. The atmosphere transports a little heat. The oceans transport a lot of heat. If you want to move heat from the equator, where the planet is warmer, to the poles where it's cooler, you do it in water. And so ocean circulation is a really vital a way that the planet regulates the balance between warm and cold areas. And the theory from this, and I don't believe it's universally accepted, is that by introducing, let's see, how do we get started on this? When the Gulf Stream travels from the warm waters of the Florida to the UK, there's a lot of evaporation and cooling. Evaporation is a cooling process. When you get out of the shower and you start to evaporate water off of you, you get the shivers because it's a cooling process. And so as water evaporates off of that warm current, it will both cool and become saltier because the salt's not evaporating, it's just the water part. So when you go from warm, salty water to cooler and saltier water, at some point up there at the northern arm of that circulation, it's going to sink. And there's just a few critical places in the world and in the North Atlantic where that sinking occurs. And the theory is that if you disrupt that northern end by introducing a lot more fresh water at the surface there, that it could either alter, reduce, and some publications even dramatically stop that global circulation pattern. Now, whether that is happening or will happen, or that's I'm not the person to speak to that, but the consequences of that would be if you stopped that circulation, or if you didn't allow the Gulf Stream to make it that far north, you would really cool off Western and Northern Europe in a really short amount of time, like a decade or two, and it would have consequences. And these thermohaline circulation fluctuations have happened before in the past, and they are considered to be related to some of the noise that we've had in the history that was earlier than that graph I showed. But that would, if it were to happen, and again, there's still a lot of back and forth on ocean circulation. If that were to happen, we would see a dramatically colder Northern and Western Europe. The Gulf Stream is what keeps the UK the UK.